Good day, everyone. We are the Group 4 and we are going to discuss about numerical differentiation and numerical integration. So these two are the basic mathematical operations with a wide range of applications in many areas. It is therefore important to have good methods to compute and manipulate derivatives and integrals. So first, what is numerical differentiation? Numerical differentiation is the process of finding the numerical value of a derivative of a given function at a given point, and it has various methods. First is the finite difference method. Second is the forward, backward, and central difference formulae. And the last one is derivatives for noisy data.
So the next topic is finite difference method. So let us first know the definition or meaning of it. A finite difference is a mathematical expression of the form f of x plus b minus f of x plus a. If a finite difference is divided by b minus a, one gets a difference quotient. The approximation of derivatives by finite differences plays a central role in finite difference methods for the numerical solution of differential equations, especially boundary value problems. Finite difference method is used to solve ordinary differential equations that have boundary conditions rather than at the initial point. These problems are called boundary value problems. So the next slide is also a meaning of finite difference method. First, the principle of finite difference method is close to numerical schemes used to solve ordinary differential equations, and it is approximate method for solving partial differential equations. Finite difference method has been used to solve wide range of problems. This has include linear and nonlinear, time independent and dependent problems. The next slide is all about the basic idea of the method. First is replace derivatives in a differential equations with approximations and solve the resulting algebraic equations to get approximate solution. So the finite difference method can also be applied to problems with different boundary shapes, different kinds of boundary conditions, and for a region containing number of different materials. The next slide is all about three basic types which are commonly considered in this topic. So first one is the one-sided or the forward difference. Second is the one-sided or the backward difference. The third one is the central difference. So the first one, forward difference, has the formula of f of a plus h minus f of a all over h. The second, one-sided or the backward difference, has the formula of f of a minus f of a minus h all over h. The sole difference has the formula of f of a plus h minus f of a minus h all over 2 times h. So that ends my report. The next reporter will discuss deeper about finite difference method, three basic types and its examples. Thank you and God bless.
Hi everyone, I am Adrian Mimoncada and I am going to discuss the forward, backward, and the central difference formulae. So first, I am going to show you how to derive these three formulas. So the forward, backward, and the central difference are all taking 2 points on a graph with the different height and dividing that by the horizontal distance. So we are basically taking the rise over the run or the slope. So as you can see here in the graph, we have a forward difference nga point A to point A plus H. So, slope, atong kwaon ang iyahang slope, which is the difference in y values over the difference of the x values. So, unsa man ang mga y values? We have a plus h minus a over run niya. Unsa man ang run? Kining x niya nga values, which is the h, kini na line. So, ang atong formula kay function of a plus h minus function of a over h. So, the second formula is the backward difference, which considering the left side of the a. So, kini siya na part. Kining a o kini diri nga line. So, to get the formula, same ra gihapon sa atong gibuhat ato ra gihapon kuon ang iyahang slope, which is the difference in y values minus over the difference in x values. So, we have a kining nga line minus a plus h over iyahang run, which is h ra gihapon. So, ang atong formula is function of a minus function of a minus h over h. So, the last one is the central difference. Central difference is the combination of the forward and the backward difference. So, here in the graph, kini nga line, kini nga part, as you can see, na iyahang na-cover ang duha ka po, ang backward o ang forward difference. So, motong ningon siya nga, it is a combination of the two. So, unsaon man pagkuha ang iyang formula, same ra gihapon. Slope ra gihapon nato. So, difference minus, difference of the in the y values over difference in the x values. So, we have kini nga line, x minus x plus h o kining minus x minus h kini siya over pila naman ang iyahang run. So naman tay duha ka h diri no kining nga line. So h plus h is equal to 2h. So moon siyang ingani atong formula nga function of x plus h minus function of x minus h over 2h. So all you have to remember is these three dayon when solving the problem of forward, backward, and central difference kay ato na dayon siyang i-substitute. Kay usually A and H is given naman na siya. So direct substitution na lang dayon ta. So to understand further, let's go ahead and answer some sample problem.
So, we have here an example. Approximate the derivative of f of x equals x squared plus 2x at x equals 3 using the forward, backward, and central difference method using h equals 1. So first step, let us identify point of interest and step size. So given we have point of interest equals 3 and 1 as our step size. Solving the other values, let us compute point of interest plus step size. We have 4 and point of interest minus step size. We got 2. So after solving these values, let us substitute 2, 3, and 4 to f of x equals x squared plus 2x. So f of x, substitute 2 equals 2 squared plus 2 times 2 equals 8. Next is ang 3 squared plus 2 times 3 equals 15. And f of 4 equals 4 squared plus 2 times 4 equals 24. So forward formula, f of a plus h minus f of a over h. So substitute point of interest plus h, we have 4, and point of interest, we have 3. So f of 4, based atong na-compute previously,
we got 24. So f of 4, 24 minus 15 sa f of 3 equals 9. Over step size 1, still we got 9. So forward difference is 9. Next is ang backward difference. F of a minus h all over h. So point of interest, we have 3. So f of 3, we have 15. And point of interest minus h, we have 2. So f of 2, we have 8. So 15 over 8, 15 minus 8 equals 7. Over 1 nga step size, still 7. So backward difference is 7. So using next is ang central difference. F of a plus h minus f of a minus h all over 2 times h. So point of interest plus h is 4. So f of 4 is 24 and point of interest minus h is 2. So f of 2 is 8. So step size 2 times 1 is 2. So 24 minus 8 equals 16. Over 2, we have 8. So central difference is 8.
Hi, so I am here to report about the derivatives for noisy data. So what is noisy data? Noisy data is a meaningless data. It includes any data that cannot be understood and interpreted correctly by machines, such as unstructured text. Noisy data unnecessarily increase the amount of storage space required and can also adversely affect the result of any data mining analysis. Noisy data can be caused by faulty data collection instrument, human or computer errors occurring at data entry, data transmission errors, limited buffer size for coordinating synchronized data transfers, inconsistencies in naming conventions or data codes used, and inconsistent formats for input fields. So here are some methods for deriving the noisy data. First is the total variation regularization, also known as total variation denoising. This is a process most often used in digital image processing that has application in noise removal. It is based on the principle that signals with excessive and possibly spurious detail have high total variation. That is, the integral of the absolute gradient of the signal is high. According to this principle, reducing the total variation of the signal subject to it being a close match to the original signal removes unwanted detail wish lists, preserving important details such as edges. The concept was pioneered by Rodin, Usher, and Fatemi in 1992, and it is today known as the ROF model. This noise removal technique has advantages over simple techniques such as linear smoothing or median filtering, which reduce noise but at the same time smooth away edges to a greater or lesser degree. By contrast, total variation denoising is remarkably effective and simultaneously preserving edges whilst smoothing away noise in flat regions, even at low signal-to-noise ratios. So here's how to solve the total variation denoising. We propose to use total variation regularization in Fu equals alpha r times u plus df times au minus f, where Ru is a regularization or penalty term that penalizes irregularity in u. Au times x equals integral of 0 x times u is the operator of anti-differentiation. Df times AU minus F is a data fidelity term that penalizes the discrepancy between AU and F. And A is a regularization parameter that controls the balance between two terms. We will thus compute the derivatives of F on 0, L as the minimizer of the functional, which we can denote as Fu equals alpha integration 0L times absolute value of u prime plus 1 half integration of 0L times the absolute value of AU minus F squared. The use of total variation accomplishes two things. It suppresses noise, as a noisy function will have a large total variation. It also does not suppress jump discontinuities, unlike typical regularization. This allows for the computation of discontinuous derivatives and the detection of corners and edges in noise data. The next method is the numerical implementation. It's a simple approach to minimizing the formula of the TVR is gradient descent. This amount to evolving to stationarity the PD obtained from the Euler-Lagrange equation, which we can denote as u t equals alpha d over dx u prime over absolute value of u prime minus a raised to the power of t au minus f. So we will not furthermore explain about this formula because this formula requires more about coding. So next is we have graph here that represent the methods we use. Figure 1. The function of x obtained from absolute value of x minus 1 over 1 half by adding Gaussian noise of standard deviation 0.05. So the next figure, figure 2, computing f with finite differences greatly amplifies the noise. So next, figure 3, the function of x denotes the differentiated with finite differences. The result is noisy and inaccurate. So next is the figure 4. Regularizing the differentiation process with the total variation produces a noiseless derivative of a correct located sharp jump. The discrepancy of the values from A plus minus 1 are due to contrast loss, an artifact of total variation method and presence of the noise. So in conclusion, we presented a method for regularizing the numerical derivative process using the total variation regularization. Unlike the previous developed methods, the TV method allows the discontinuities in their derivatives as desired when differentiating the data corresponding to the non-smooth function. We use the log diffusivity algorithm, which enjoys the proven convergence properties with the implementation that works rapidly for small problems and a second more suitable for large problems. The TV regularization allows the derivatives to capture more features of data while adjusting the regularization parameter controls the scale of function fluctuation in data that are ignored. So, in the derivatives of noisy data, the best method we should do is the TVR or the total variation method. So that's all. Thank you.
Next is the numerical integration. Numerical integration is the approximate computation of an integral using numerical techniques. The numerical computation of an integral is sometimes called quadrature. So numerical integration has various methods. First is the Euler's method, second is the trapezoidal rule, And the last one is the Simpson and Gaussian quadrature schemes.
Good afternoon. I'm from Group 2 and I was assigned to report this certain topic, which is Euler. Who is Euler and what did he do? He invented the calculus of variation, including its best known result, the Euler-Lagrange equation. Euler pioneered the use of analytic methods to solve number theory problems. In doing so, he united two disparate branches of mathematics and introduced a new field of study, analytic number theory. Now, what is Euler-Lagrange equation? Euler-Lagrange equation is a second-order partial differential equation whose solutions are the functions of which a given functional is stationary. It was developed by Swiss mathematician Leonard Euler and Italian mathematician Giuseppe Louis Lagrange in the 1750s. Now, what is analytic number theory? Analytic number theory is the branch of the number theory which uses real and complex analysis to investigate various properties of integers and prime numbers. Examples: topics of failing under analytic number theory include Dirichlet L-series, the Riemann zeta function, the totient function, and the prime number theorem. Why E is used in math? The number E is one of the most important numbers in mathematics. E is an irrational number. It cannot be written as a simple fraction. E is the base of natural logarithms invented by John Napier. E is found in many interesting areas, so it is worth learning about. Oh, dili gid ni suwat as fraction ang E kay ang value aning E kay 2.718281828. Dili siya ma-written as fraction. One, based ni siya sa mga natural logarithm. Gamit sa di siya sa pag-solve na itong kuan, cancellation of E raised to ln was known as 1. Ano, mga logarithms. Euler's formula, named after Leonard Euler, is a mathematical formula in a complex analysis that establishes the fundamental relationship between the trigonometric function and the complex exponential function, where the formula is e raised to ix equals cos x plus I sin x, where e is the base of natural logarithm and I is the imaginary unit and x is the angle in radians. Euler's formula relates the complex exponential to the cosine and sine functions. This formula is the most important tool in AC analysis. It is why electrical engineers need to understand complex numbers. Pero kining mga trigonometric functions, dili gini siya nga ingon nga easy to understand. Kinahanglan jud ta mag-study from basic to complex. Usa man kuno na sila na complex niagi na sad kuno sila basic, pero antud karon maglisod gyapon kog solve using trigonometric function, pero maglisod gali mig apply ani sa AC analysis sa electrical, pero formula man. Ora na, thank you.
Euler's example: y prime plus 2y equals 2 minus e raised to negative 40 where x is 0 and y equals 1. Use Euler's method with a step size of h equals 0.1 to find approximate values of the solution at t 0.1, 0.2, 0.3, 0.4, and 0.5. Compare them to the exact values of the solution at these points. Ang kani nga solusyon gikan ra din ni problem gikan ra sa Google akong gikuha. This is a fairly simple linear differential equation, so we'll leave it to you to check that the solution is y of t equals 1 plus 1 half e raised to negative 4t minus 1 half e raised to negative 2t. In order to use Euler's method, we first need to rewrite the differential equation into the form given in 1. Y prime equals 2 minus e raised to negative 4t minus 2y. From this, we can see that f of t and y equals 2 minus a raised to negative 4t minus 2y. Also note that t sub 0 equals 0 and y sub 0 equals 1. We can now start doing some computation. F of 0 equals f of 0 and 1 equals 2 minus a raised to negative 4 multiplied by 0 minus 2 times 1. Ang nakita ninyo nga value sa t sa babaw nga gikan diri sa original equation from the top kay ang t equals daw sa 0 and y equals sa 1. Pag substitute niya, ang nigawas is negative 1. Y sub 1 equals y sub 0 plus hf sub o equals 1 plus 1 equals 1 plus 0.1 multiplied by negative 1. Gikuha na siyang negative 1 which is value sa f sub 0 gikan sa babaw nga negative 1 multiply sa h which is 0.1. Balik ta ang gikan na ang h diri na siya sa 0.1. And then nakakuha siya 0.9. So the approximation to the solution at t sub 1 equals 0.1 is y sub 1 equals 0.9. At the next step, we have f sub 1 equals f of 0.1 and 0.9 equals 2 minus a raised to negative 4 multiplied by 0.1 minus 2 multiplied by 0.9. Sa nakita ninyo, ang kanang t and y gi-substitute ra gihapon siya sa value nga gihatag diri sa given, which is the value of t is 0.1 and 0.9. Then from y sub 2 equals y sub 1 plus hf1 equals 0.9 plus 0.1, which is h is 0.1, din ang value diri gikan sa babaw nga f1 is negative 0.47032 and something. Muna siya gi-multiply, then nakakuha na siya answer sa y sub 2 nga 0.852967995. Therefore, the approximation to the solution at t sub 2 equals 0.2 is y sub 2 equals 0.852967995. And that is the example for Euler's.
Good day, everyone. Today, I'm going to be discussing about the trapezoidal rule. This technique is a much more accurate way to approximate area beneath a curve. It uses trapezoids from the word itself, trapezoidal, rather than rectangles. So this is our graph. So the area beneath this curve is measured or estimated by adding all of the areas of the trapezoids here. So we have 1, 2, 3, and 4. And the change of width is denoted as the change of x. Let f be continuous on a and b. The trapezoidal rule for approximating the integral of a function of x dx evaluated from a to b is given by delta x over 2 times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3 plus f of x sub 4, where delta x is equals to b minus a over n, and p is our set of intervals. And one thing to remember, the coefficients in the trapezoidal rule follow the pattern 1, 2, 2, 2, 2, 2, 1. So as you notice, the first and the last term has the coefficient of 1, while the in-betweens has 2. So here's our example. Use the trapezoidal rule to estimate the integral of x squared dx evaluated from 0 to 1 using 4 subintervals. So first, we need to find our delta x, which is 1 minus 0 over 4 is equals to 1/4. And as you can see, I have made here a table. This is our interval, and this is our value of a function of x. So 0 squared is 0, 1/4 squared is 1 over 16, 1/2 squared is 1/4, and 3/4 squared is 9 over 16, and 1 squared is 1. So here's our formula. Plugging in, we have the answer of 11 over 32, which is the estimated area beneath the curve. Another example, approximate the area beneath f of x is equals to x squared plus 1 on the interval 0 and 3 using the trapezoidal rule with n is equals to 5 trapezoids. So here's the drawing. Again, we need to find our delta x, which is b minus a over n is equals to 3 minus 0 over 5 is equals to 3 feet. And this is our interval using number line. So our formula, plugging in, we have the answer of 12.18, which is the estimated area beneath the function of x squared plus 1. Next, absolute and relative error. An important aspect of these numerical approximation rules consists of calculating the error and using them for estimating the value of a definite integral. We first need to define absolute error and relative error. So, if b is our estimate of some quantity having an actual value of a, then the absolute error is given by the absolute value of a minus b. And the relative error is the error as a percentage of the actual value given by the absolute value of a minus b over a times 100. So example, calculate the absolute and relative error in the estimate of the integral of x squared dx evaluated from 0 to 1 using the trapezoidal rule found in our example. So our a, or the calculated value, is 1/3. B, or the estimated value, is 11 over 32. Plugging in, we have 1 over 96 or 0.0104. So this is our absolute error. And for the relative error, we have A, which is 1/3 or the calculated error, and the absolute error, which was 12, 1 over 96. So our relative error is 1 over 96 divided by 1/3 times 100% is equals to 3.1%. So this is our relative error. That's all. Thank you.
So for the last numerical method, we have Gaussian quadrature. A Gaussian quadrature is an approximation of the definite integral of a function usually stated as a weighted sum of function values at specified points within the domain of integration. So I is equals to the integral of a to b f of x dx, where f of x is the integral and a is the lower limit of integral and b is the upper limit of the integral. So as you can see, naatay figure 1 nga trapezoidal rule, then ang figure 2 kay Gaussian quadrature. So sa trapezoidal nigamit siya og straight line from x sub 1 to x sub 2 while sa Gaussian quadrature ang x sub 1 o x sub 2 niya wala siya sa point A and B. Pero ang x sub 1 o x sub 2 na to is symmetry na sila ang duha. So same sila og distance from the origin. So the origin is the center of the symmetry. So ang word nga symmetry is murag dili na bago sa ato kay naaman ni siya sa ato ang mathematics in a modern world. So ang ang pasabot niya sa symmetry is from the center to the from the center to x1 nga distance niya is mirror siya or the same siya sa center to x sub 2. So mo na siya ang pasabot. So for the formula, the integral form of a Gaussian quadrature formula is the integral from -1 to 1 f of x dx is approximately equal to the summation of c sub I f of x sub I where ang atong I is equals to 1. So, ang x na to, muna siya atong nodes, dayon ang c sub I na to is muna siya atong weights. So this integral formula is exact for polynomials of degree up to 2n minus 1. So kaning 2n minus 1 muna tong gamiton para makahibaw ta kung pila ang atong degree of precision. So the integral from -1 to 1 f of x dx is approximately equal to c sub 1 times f of x sub 1 plus c sub 2 times f of x sub 2. So, continuous yan until c sub n times f of x sub n. So, para mas makasabot ta, continue ta. So, consider n is equals to 2 and a and b is equals to -1 and 1. We want to determine the x sub 1, x sub 2, c sub 1, and c sub 2 so that the quadrature formula, which is the integral of -1 to 1 f of x dx, which is approximately to c sub 1 times f of x sub 1 plus c sub 2 times f of x sub 2 has a degree of precision nga 3. Giyon sa nato pagkahibaw sa degree of precision nga 3. So we use the polynomial degree which is 2n minus 1. So natay given value nga n is equals to 2. So 2 times 2 minus 1 is equals to 3. Munang naatay degree of precision nga 3. Magamit nato ng degree of precision dire sa solution. So kay niingon man tag degree of precision nga 3 kay 3. So gikan dire sa x magleta f of x is equals to x. Dara mag-start atong counting. So 1, 2, then 3. Ang kaning let f of x is equals to 1, wala na siya appeal sa degree of precision. Like if maingon kag degree of precision nimo is 2, included na siya sa pag-solve pero wala na siya appeal sa pag-count kung asa nag-start imong degree of precision. Muna siya ipasabot. So for the solution, let f of x is equals to 1. We have c sub 1 plus c sub 2 is equals to 2. So ang kaning 2 na to is makuha na to na siya using the calculator. So integral, ang ato ang lower limit is -1. Ang upper limit na to is 1. Dayon, i-type na to ang 1, dx is equals to 2. So next, we have let f of x is equals to x. So we have c sub 1 times x sub 1 plus c sub 2 times x sub 2 is equals to 0. So maglatag f of x is equals to x sub 2. We have c sub 1 times x sub 1 squared plus c sub 2 x sub 2 squared is equals to 2/3. So next is we have let f of x is equals to x cubed. So c sub 1 times x sub 1 cube plus c sub 2 times x sub 2 cube is equals to 1. So natay equation 1, 2, 3, and 4. So ang kani nga mga equation, ato na siyang gamiton para ma-solve na to ang x sub 1, x sub 2, c sub 1, ag c sub 2. Diba, if naatay, makita natin rin, naatay upat ka unknown, which is kaning x sub 1, x sub 2, c sub 1, c sub 2. Munang kinahanglan ta og 4 equations kay naaman tay 4 unknowns. So, naana tay, so ato siya ibutang sa formula. We have the integral of negative 1 to 1 f of x dx is approximately equal to f of negative square root of 3 over 3 plus f of square root of 3 over 3. So, if nag-wonder mo, asa giunsa ni siya pagkuha ning negative square root of 3 over 3 o ganing square root of 3 over 3, so ginaan na siya pagkuha. So, naatay katong 4 equations, right? Sa first equation, atong tanawon sa first equation, naatay c sub 1 plus c sub 2 is equals to 2. So, makaingon jud ta nga ang atong c sub 1 is equals to 1. Ang atong c sub 2 is equals to 2. So, makaingon ta nga ang c sub 1 ug c sub 2 is equals siya. Nga pareha silang duha, nga ilahang value kay, silang duha is equals to 1. Sakto ba? So, next. Manita sa equation 2. So, kung mayroong tag-equal ang atong c sub 1 o c sub 2, sakto ba nga equal sa datong x sub 1 o x sub 2? Sakto, right? So, ang atong x sub 1 is equals x sub 2. So, kay niingon man ta ganina nga ang x sub 1 is symmetry sa x sub 2. So, dapat ang atong x sub 2 is negative para masymmetry siya sa x sub 1. Kaya dapat symmetry man silang duha. So, arita sa equation 3. Ato ang i-substitute ang mga value nga aton hibaw-an. So, we have 1 x sub 1 squared plus 1 times x sub 1 squared is equals to 2/3. So, makuha ta nga atong x sub 1 is equals to negative square root of 3 over 3. Nya, ang atong x sub 2 is square root of 3 over 3. So, here we have an example para mas masabtan nato siya. So, use 2-point Gauss quadrature rule to approximate the distance covered by a rocket from t is equals to 8 to t is equals to 30 as given by. So, x is equals to the integral from 8 to 30, 2,000 ln times 140,000 over 140,000 minus 2,100t minus 9.8t dt. Also, find the absolute relative true error. So, atong tan-awon kung pila ka percent iyang error. So, sa solution, first change the limit of integration from 8 and 30 to negative 1 and 1. So, natay the integral of from 8 to 30 ft dt is equals to 30 minus 8 over 2. The integral from negative 1 to 1 f of 30 minus 8 over 2x plus 30 plus 8 over 2 dx. So we have 11, the integral from negative 1 to 1, f of 11x plus 19 dx. So next, we get weighting factors and function argument value from table 1 for the 2-point rule. So if nag-wonder mo nga asa gikan, so muna ganina katutong gi-solve nga c sub 1 and c sub 2 is equals to 1 and ang atong x sub 1 and x sub 2 is equals to square root of 3 over 3. Muna siya. So now we can use the Gauss quadrature formula. So we have 11, the integral from negative 1 to 1, f of 11x plus 19 dx is approximately equal to 11 times c sub 1, f of 11x sub 1 plus 19 plus c sub 2 times f of 11x sub 2 plus 19. So next itong gibuhat is itong gi-substitute ang value sa x sub 1 o x sub 2. So we have 11 times f of 11 times negative 0.5773 plus 19 plus f of 11 times 0.5773 plus 19. So we have kaning 12.64915 o kaning usa kay 25.35085. So nang wonder mo nganong nahimo siyang 296.88317 og 708.4811 ginani siya pagkuha. So, di ba natin value ganina ang x is equals to 2,000 ln times 140,000 over 140,000 minus 2,100 t minus 9.8 t mo na siya. Ang atong t is katong ato ang 12.664915 and 25.35085. So nakuha na to ang 296.8317 ug 708.48111. So muna siya. Atong gi-add ang duha, then atong gi-times og 11, nakakuha tag 11,558.44 meters. So the absolute relative true error. So ang true value gid niya is 11,061.34 meters. So para makuha na to ang error, atong i-minus ang true value, i-minus na to siya sa atong nakuha, then i-divide na to sa true value, then i-times na to siya og 100. So equal siya 0.0262%. Muna siya ang error. So I hope nga naamoy nasabtan, and thank you. So for another numerical method, Simpson's rule. Simpson's rule is another area approximating tool. Simpson's rule is a numerical method that approximates the value of definite integral by using quadratic functions. This method are more accurate than the other numerical approximation, since it uses quadratic phenomenons to approximate function. Simpson's rule actually gives exact result when approximating integral of phenomenons up to cubic degree. So Simpson's rule also uses parabolic arc instead of straight line segment used in trapezoidal rule. So, kano siya nga figure, mo na siya ang example sa Simpson's rule. As you can see, naka-parabolic arc siya. While a trapezoidal is from point A to point x sub 1 is ayang gigamit kay straight line. Mo na siya ang rason nga nung makaingon ta nga mas accurate jud ang Simpson's rule kay kung trapezoidal gud since naaman siya kanang mga gagmay nga space, mo na siya ang makakos sa error. But ang Simpson's rule nasa siya mga error pero dili siya na nakadako ang ihang error. So for the formula, we have the definite integral from a to b, f of x dx is approximately equal to s sub n, where s sub n is delta x over 3 times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2, and then continuous siya, niya kanay second from the last is 4 times f of x sub n minus 1 plus f of x sub n. So, ang delta x na to is equals to b minus a over n. So, kani siya, mo ni siya atong example de sa kaning Simpson's rule. Approximate the area beneath f of x is equals to x squared plus 1 on the interval 0 to 3 using Simpson's rule with n is equals to 6 sub-interval. So, the integral of 0 to 3, x squared plus 1 dx. So, atong kuhaon ng delta x is equals to 3 minus 0 over 6 is equals to 1/2. So, ang gibuhat na ako siyang gitable para mas dali. But usually, sa mga examples nga makita, ang ilang gigamit is kanang number line, but kani, akong gi-table siya kay para mas dali gani. So, ang value sa itong x is 0, 1/2, 1, 3 over 2, 2, 5 over 2, and 3. So, as you notice nga, 1/2 ang iyahang difference. So, ato siyang i-substitute sa f of x, which is x squared plus 1. So, muna ni ang iyang answer, 1, 5 over 4, 2, 13 over 4, 5, 29 over 4, and then 10. So, ito siyang i-substitute sa katong formula. So, muna siya. Nahima siyang 1/2 over 3 times 1 plus 4 times 5 over 4 plus 2 times 2 plus 4 times 13 over 4 plus 2 times 5 plus 4 times 29 over 4 plus 10. So, ito siya i-calculator. Ang answer niya is 12. So, para ma-check na to siya, if accurate ba gid siya, sa kaning nga problem ra ha, kay di man jud tanan pareha. Mogamit ta og katong sa calculator, integral din natong i-type sa x squared plus 1 dx, then iyahang 0 to 3. So, ang makakuha nimo nga answer is 12. So, makaingon jud ta nga accurate ang Simpson's rule. But sa kanila nga problem, kaya na may mga problems nga dili jud accurate, pero kana laging gamay ra jud pod iyahang error.